The derivative is the main core of differential calculus. Before working on the different formulations, let us find derivatives through limits. Welcome to differential calculus. Just what are derivatives? Derivatives are what differential calculus is all about, which shows that this subject talks about changes. It determines the rate of change. In a curve, one can determine the rate of change of a tangent line from one point to another, and that is derivative. Say that we take point 1 from the curve. This point has an x-coordinate we denote as x sub 1, and y-coordinate denoted as f of x sub 1. We are to determine the slope of its tangent line. But since we only got one point, that would be difficult if done algebraically. So we then mark another point 2 from the curve. This point is really near the first point. Point 2 has an x-coordinate of x sub 2 and y-coordinate of f of x sub 2. Connect the 2 points to create a secant line. From here, we can then use the formulation of slope, which is rise all over run, or change in y over change in x. From the illustration, we get slope as f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Now, to avoid so many variables, we note that x sub 2 is just x sub 1 plus change in x. And having denoted this, we can also write the y-coordinate as the function of x sub 1 plus delta x. Place this into the equation to get f of x sub 1 plus delta x minus f of x sub 1 all over x sub 1 plus delta x minus x sub 1. Take note too that x sub 2 minus x sub 1 is actually the change of x. We denoted this as delta x. So the slope equation is simplified as f of x sub 1 plus delta x minus f of x sub 1 all upon delta x. Now remember that the slope formula we derived is for the secant line, but we are looking for the tangent line's formula. This is where we use limits, as we will attempt to make the secant line into tangent line, as we move point 2 at the position of point 1. That is through the idea that delta x should be 0. And we transform the slope equation by adding a limit as delta x approaches 0. The limit of delta y over delta x is then taken as dy over dx in calculus, which is read as the derivative of y with respect to x. Later on, dy over dx can also be denoted as y prime. Because we are just starting with calculus, a lot might be wondering how difficult the process can get. However, there is a simple algorithm of figuring out the derivative using limits. First is to replace the x variable with x plus delta x, and y is replaced with y plus delta y. The next step is to transpose y to the other side, where the terms will be subtracted from the transform expression. Furthermore, divide the simplified equation by delta x, and lastly, add the limit where delta x approaches 0. Get used to the algorithm through polynomial examples. First, we are to find the derivative of the function y is equal to x squared plus 3x minus 2. The first step is to transform x and y, making the function y plus delta y is equal to the square of x plus delta x plus 3 times the quantity of x plus delta x minus 2. Eliminate groupings by expanding the terms. The square of x plus delta x becomes x squared plus 2x delta x plus the square of delta x. The second term becomes 3x plus 3 delta x. Then add 2. There are no similar terms at this point, so we can proceed to transposing y to the other side of the equation. But then, y was defined from the premise as x squared plus 3x minus 2. So the equation turns into delta y is equal to x squared plus 2x delta x plus the square of delta x plus 3x plus 3 times delta x minus 2 minus the quantity of x squared plus 3x minus 2. Take out the parentheses once more to have delta y is equal to x squared plus 2x delta x plus delta x squared plus 3x plus 3 times delta x minus 2 minus x squared less 3x plus 2. This equation already has similar terms which cancel out. They are x squared, 3x, and 2. So the equation is now simplified as delta y is equal to 2x delta x plus the square of delta x plus 3 times delta x. We move to step 3, which is to divide everything by delta x. And notice that there are some terms on the right which can be reduced. So delta y over delta x is taken as 2x plus delta x plus 3. The last step is to add a limit as delta x approaches 0, which zeroes out the second term on the right expression. So the derivative of y with respect to x, or y prime, is 2x plus 3. The second example has the function y is equal to 2x cubed minus 7x plus 1. Again, transform the variables, making the equation y plus delta y is equal to 2 times the cube of x plus delta x minus 7 times the quantity of x plus delta x plus 1. Before doing the others, we expand those terms inside the parentheses. And note that the cube of a binomial is easily expanded when we use Pascal's triangle, which gives the coefficients 1, 3, 3, and 1. So the equation becomes y plus delta y is equal to twice of x cubed plus 3x squared delta x plus 3x delta x squared plus the cube of delta x. Then the second term can be expanded as negative 7x minus 7 delta x plus 1. Next is to distribute 2 in the first term and transpose y to the right expression. So delta y becomes twice of x cubed plus 6 of x squared delta x plus 6x delta x squared plus 2 delta x cubed minus 7x minus 7 delta x plus 1 minus y. The premise states that y is 2x cubed minus 7x plus 1. So delta y becomes 2x cubed plus 6x squared delta x plus 6x delta x squared plus twice of delta x cubed minus 7x minus 7 delta x plus 1 minus y, which is the quantity of 2x cubed minus 7x plus 1. Reduce the equation by reducing similar terms like 2x cubed, 7x, and 1. The function then turns to delta y as equal to 6 squared delta x plus 6x delta x squared plus 2 times the cube of delta x minus 7 delta x. As this is already the simplified equation, we proceed to step 3, which is to divide the function by delta x. And this step cancels out many parts of the equation, resulting to delta y over delta x as equal to 6x squared plus 6x delta x plus 2 times delta x squared minus 7. Then move to the last step where we determine the function's limit as delta x approaches 0, which is basically to zero out terms with delta x. Thus, the derivative of y with respect to x is 6x squared minus 7. Example 3 includes another polynomial, y is equal to x raised to 4 minus 2x cubed. First, transform x and y, and have y plus delta y is equal to x plus delta x raised to 4 minus 2 times x plus delta x cubed. And since the binomials are raised into 4 and 3, the easiest way to expand them is to use Pascal's triangle. Or you can also expand them through binomial theorem. With Pascal's triangle, the cube of a binomial has the coefficients 1, 3, 3, and 1. Then the expanded form of the fourth power of a binomial has the coefficients 1, 4, 6, 4, and 1. Place these expanded binomials into the function and distribute the external factors to have y plus delta y is equal to x raised to 4 plus 4x cubed delta x plus 6x squared times the square of delta x plus 4x times the cube of delta x plus delta x raised to 4 minus 2x cubed minus 6x squared times delta x minus 6x times delta x squared minus 2 times the cube of delta x. There are no similar terms as of the moment, so transpose y to the other side, and again, y is in terms of x from the premise. By subtracting y, which is x raised to 4 minus 2x cubed, a couple of terms are cancelled out. The reduced function is delta y is equal to 4x cubed delta x plus 6x squared delta x squared plus 4x times the cube of delta x plus delta x raised to 4 minus 6x squared delta x minus 6x times the square of delta x minus 2 times the cube of delta x. The function is still seemingly long, but then it has already been reduced. So take step 3 of dividing the function by delta x, which makes the function into delta y over delta x as equal to 4x cubed plus 6x squared delta x plus 4x delta x squared plus the cube of delta x minus 6x squared minus 6x delta x minus 2 times delta x squared. Then the last step is to inject the limit as delta x approaches 0 into the function, where this step will zero out terms with delta x. Then we get dy over dx as 4x cubed minus 6x squared.